Now, so if it is a situation where the fluid is electrically neutral, so we are going to start now. Fluid is electrically neutral and there is no gradient in ionic species. So, this is the Ohm's law, I equal to nu E, as we have derived before. So, and this Z I square N I is the average or net number density, or Z I square C I is the net molar concentration of the electrolyte. So, this is the, if I call this is the C0, is also can be mentioned or can be considered as a bulk value. Now, from this the current density equation, we can derive the conservation of charge density, and equation for the charge density can be derived this way. So, now charge density we have defined as rho e equal to governed by this relation F into Z I C I. C I is the molar concentration of ith ionic species. So, if I multiply with that, and this is the relation. So, I get a situation in the ionic flux of the ith molar flux of the ith ionic species. So, if it is multiplied with Z I, F Z I, so which is nothing but the previous one I. So, we get a equation like this, del rho E del T plus divergence of I equal to 0. So, this is referred as the conservation or charge transport equation. Now, if it is a steady state, we have time derivative is 0. So, what we have is divergence of I is 0 at any point within the electrolyte medium. So, this is also referred equation of continuity of current density in steady state. We can say this as the continuity equation for the current density. Now, if you have the electrically neutral and time independent and convective terms vanishes, and the charge conservation equation reduces to this form, because what you have here, this goes, time derivative goes. So, if I take the divergence in both sides, so you get a situation like this way. Okay. So, these are the some important transport equations to characterize the electrokinetics of ionized liquid. So, as we could see, the equation of ionic transport equation for ionic species is involving U. It is involving the E electric field. So, this electric field is governed by this, if we just look back, electric field is governed by this Poisson equation, and this Poisson equation is also involved in the equation of fluid flow. So, that means all these equations are coupled. So, that means the solution of the or the form of the velocity or the ion distribution and the electric field are interrelated. Now, if I write this equation in a Cartesian coordinate form, the transport equations, which we refer as the Navier-Stokes equation for the incompressible Navier-Stokes equation, we get a situation like this way. Here, this is the electric body force term. Other things are usual situation for usual Newtonian incompressible fluid flow equation. So, if there is a pressure difference occurs, and if there is a flow, there will be a non-zero pressure gradient, and the continuity, this is the x momentum or u momentum equation, this is a v or y direction, this is the z direction. So, here we have 3 component of velocity and rho e is a charge density. Obviously, rho e is not a constant also, because it involves the molar concentration of the ionic flux, which may vary in the space, vary with x, y, z. So, the other equation, the equation for ion transport, is referred as the Nernst-Planck equation. So, this Nernst-Planck equation for the ith ionic species is now can be expressed in Cartesian coordinate this manner. Okay. Now, here we may have a number of ionic species. So, each ionic species will obey this equation, and the valence is Z I. So, and once I get the C I at any point for all these i's, so one can get the charge density rho e, and then one can write the equation. So, obviously, this equation is related or depending on this equation of ion transport equation is also referred as the Nernst-Planck equation. And these equations, this set of equations are supplemented by the Poisson equation for electric field, which we have derived already. So, what I find that this is a linear equation, of course, but other equations, see, these equations are all nonlinear, second order, and quite a complicated situations. So, it is involving this kind of elliptic form because of this Laplacian, and also it has a hyperbolicity because of this kind of first order gradients. So, you have u dot grad situation. So, this is a complicated and is also nonlinear. So, solving this kind of set of equations are quite complicated situation. Now, to simplify that, so there are several ways one can simplify. So, one of the simple way is the considering a situation where we have the equilibrium situation, that means there is no flux of ions. That means this is written wrongly, it should be NCI dot n equal to 0. So, here it should be NCI dot n equal to 0 and in a steady state situation. So, if I assume that ion flux is 0 ion flux, and you have the convective fluid velocity is 0, okay, and 0 flux of ions, if I assume this kind of situation. So, then we can reduce this Nernst-Planck equation to this form for any ionic species given by this way. Okay. So, that means if I have this is the normal direction is x direction here, normal direction we have considering is the x direction, and this is the plane is x equal to 0 plane, say. So, this is a surface. So, what you have is ion flux normal to this is 0, and you have a electric field across this parallel to the surface. So, in this case we can write the Nernst-Planck equation in a simplified form as this. Now, this can be clubbed or integrated, simplified to this form, and we get an integral of this equation given by this. Now, this Ci 0 we call the bulk concentration, that means at x equal to 0, where integration constant is taken care by the Ci 0, where we measure the say electric potential is becoming constant or 0. Because another thing is that electric potential can have a non-zero value, but if it is a constant. So, if we subtract from the electric potential, because electric potential appears in a gradient manner, gradient form. So, if we subtract a constant from the electric potential phi, so it satisfies the same equation as the equations phi minus zeta or phi minus constant satisfy, or the same equation by the phi itself. Okay. So, the solution of this equation can be expressed in this manner. Now, if I substitute in the Poisson equation, that means here we are considering a binary electrolyte, and let us take monovalent electrolyte, that means Z plus equal to minus Z minus equal to 1. So, that means the valence is taken to be 1. So, it is containing two species, a monovalent cation with concentration C plus and monovalent anion with concentration C minus with identical bulk concentration, because if we assume the bulk electroneutrality, so what we should have is C plus minus C minus equal to 0. So, you have this. Okay. So, C 0 is the bulk concentration if I assume. So, we can have a we can write this equation in this form, and so this sine hyperbolic, as you know, sine hyperbolic x equal to e to the power x minus e to the power minus x by 2. So, this technique if we apply, so this equation 14 can be reduced to a equation like 15. So, this equation is referred as the Poisson-Boltzmann equation. So, again this is a nonlinear equation, because phi is involved over here in a nonlinear fashion, but once I get the phi, I get the distribution of ions by this Boltzmann equilibrium Boltzmann distribution. So, obviously, this model, this is also referred as the Poisson-Boltzmann model. So, this Poisson-Boltzmann model are based on few simplified assumption. First of all, what we have assumed that the distribution of ions and phi are under an equilibrium condition, and no bulk flow, fluid flow is assumed. So, obviously, here what we find that this is decoupled from the Navier-Stokes equation. So, that means whichever way the fluid velocity is developed, so this equation for electric field and the ions are independent of the Navier-Stokes equation or the local fluid velocity. Okay. So, that is the simplicity of the Boltzmann equation. Now, what we will discuss about the Debye layer thickness. Now, what we talked about, that when there is a aqueous media which is in contact with the solid surface. So, there will be a formation of diffuse layer, Stern layer and a diffuse layer, which we totally called as the Debye layer. So, now this phenomena is also called the screening. That means, you have a situation where the surface charge has been screened by the Debye layer formation. Now, we would like to measure the screening length. So, that means, what we can say is the Debye layer is such a length scale that beyond which the this charge density has no effect on the fluid. Okay. Now, so Debye length is a distance. This is the way we can define. The Debye length is the distance over which a charge is shielded by the ions in a solution. In other words, beyond the Debye lengths, away from the fixed charges, their effect on the medium is vanishingly small. So, now if we consider a situation only one dimension, that means here you have the x is this direction. So, what we can write the this equation from here, we can write as this is the Poisson equation. So, d2 phi dx2 equal to charge density by epsilon e. So, this is written as this. Now, if I assume that the ions are obeying the Boltzmann distribution, which is governed by this equation, and so the charge density becomes 2c0 f sin hyperbolic phi f by RT. Now, here we make an assumption. We assume that the phi is quite small. Okay. If phi is small, smaller than f by RT, no, phi is smaller than RT by f. So, that means what we can do is we can approximate this sine hyperbolic phi f by RT is becomes f by RT phi. Okay. So, if I do this approximation, if we assume phi is to be small, so in that case what I get that rho e can be simplified, this equation can be simplified to this form. So, this is a linearization. So, that means this is the linearized Poisson-Boltzmann equation is governed by this equation. This is also called the Debye-Huckel approximation, which we will talk little bit later subsequently. Now, we have the differential equation d2 phi dx2 equal to 2c0 f square by epsilon e RT. Now, we define a length scale, say lambda, which is equal to root over epsilon e RT by 2c0 f square. Epsilon is the permittivity. So, if I define a length scale like this way, or some parameter say lambda, so what I can write now this equation as d2 phi dx2 equal to lambda square phi. So, the solution is phi equal to a e to the power is here, this is lambda square. So, this will be the inverse way. So, this is minus 2. So, phi by lambda square. So, minus 2. So, e to the power x by lambda plus b e to the power minus x by lambda. So, lambda to the power minus 2 or phi by lambda square. Okay. Now, the conditions are whatever is given is phi equal to 0 as x tends to infinity, because the electric potential in the bulk it is neutral, whatever the value I can take subtract from this phi, and we can take phi equal to 0 in material of whatever the constant value, because phi approaches a constant. So, this implies that a is 0. Now, if you have phi equal to zeta at x equal to 0, so you get b equal to zeta. So, phi equal to zeta means you have a constant potential on the surface x equal to zeta. So, from here we get an equation as this form. We get an equation that is phi now phi x equal to zeta e to the power minus x by lambda. Okay. Let us take this one. So, phi becomes phi x equal to zeta e to the power minus x by lambda. Now, this shows that if when lambda becoming small, so that means you have this becoming large x by lambda. So, if lambda is many times less than 1, so x by this term is tending to 0 as lambda becoming many times less than 1. So, that means beyond the Debye length, so lambda we define, so far we have not defined anything, we define lambda as the Debye length. So, lambda how we have defined is root over epsilon E r t by 2 C 0 f square. So, what it shows is that the Debye length is depending on the bulk molar concentration of the electrolyte. So, given an electrolyte with the permittivity epsilon E, we can find out the Debye length, which gives an estimate that up to which the length the charge which is situated at the surface are screened, up to which length. Okay. So, we can say that x becoming larger than the Debye length, we will have the charge density tending to 0. Now, so far we have discussed about the transport equations. So, now we have to see the boundary conditions, which we can impose the boundary conditions on this kind of to analyze the flow problem, because we have the partial differential equations. As we could see here, you have a second order elliptic type of equations. So, that means all the boundary conditions for x, y, z are need to be given. So, always we have a Laplacian operator or elliptic type of form. So, this demands that the boundary conditions are need to be prescribed in order to get a solution for this kind of equations. Now, how the boundary conditions are developed are governed. Now, boundary condition means we have a rigid surface over which, say, we consider a ion impermeable rigid surface. So, rigid surface which is ion impermeable as written. So, that means what we have is no normal flux of the ion across the surface and the velocity across the surface is 0. So, n here we are is the measuring, or n is denoting here is the unit outward normal to the boundary. So, we have these two conditions u dot n equal to 0 and n ni or n c I dot n equal to 0. So, this n ni equal to 0 the rigid surface. So, no normal flow and n ni this flux across the surface. So, 0 flux on the surface. So, this gives you the later condition gives you del n ni n plus z I f by r t, sorry, this is f by r t, f by r t n I del phi del n equal to 0. So, this is the two conditions, or combinedly I can write as equation 1. Now, if we have del phi del n is 0, so that means no gradient in electric field. So, we can simply write del ni del n equal to 0. So, this again will give you the Boltzmann distribution. Now, let us consider a surface charge on the surface rigid surface, you have a surface charge density. So, let the surface have a charge density sigma s and the electric permittivity of the solid be epsilon 2. Now, we have a situation say here. So, which is the interface between two or over which the liquids are flowing. So, let us call this liquid which has a epsilon E and the potential is phi. Now, we know that del cross E equal to 0 everywhere. So, we construct a control volume or a arbitrary area, say in 2 dimension A, B, C, D. Let us take this A, B, C, D, okay, arbitrary area which contains the interface. Okay. And now, we construct a surface S with base curve as ABCD. Say a cylinder, square cylinder or a closed surface with base curve as ABCD. So, now del cross E equal to 0 everywhere. So, if I now apply the Stokes theorem, so del cross E ds can be written as the contour integration or integration over these curve ABCD of E dot dl. dl is the line element on this. So, what we have is integral ABCD E dot dl equal to 0. Okay. Now, say this is the surface n. Now, let this distance is a, height is a, this is also we take as symmetrically. So, this is a and this is b. So, when we curve, so this is equal to integral of over a b plus b c plus c d minus a d, a b plus b c. So, it will be a some direction. Now, when I am integrating this E dot dl, so the line element here it is says this is x axis and perpendicular is y. So, here it is dy, and so that means you have here integral over a b e y dy, you have the component this plus integral over b c e x dx plus integral over c d e y dy minus integral over a d e x dx equal to 0. Now, these two are will be the equal and opposite. So, what we left over is integral this is because we assume that these are infinitely small. So, ABCD, this ABCD is a infinitely small control volume. So, the on the surface we neglect any change of this E x E y components. So, from here I can write now if here this is within the solid zone and if I denote this as the with superscript 2 or subscript 2 and this is with subscript 1. So, what I can write now when I am on B C. So, this is B into E 1 x and this is will be B into E 2 x equal to 0. So, this gives you del phi 1 del x equal to del phi 2 del x. So, this is the continuity condition of the electric field at the interface. So, the next one will carry it forward to the next lecture.